Hello, today we're going to be looking at surds. You might have heard the word surd before. One thing I would do if you're in front of me would I say like what is a surd? And we're going to do an introduction. This is all going to be non-calculator. Very easy to just put numbers in your calculator and get it to do stuff, but it's about understanding the idea of surds and not just having a machine do the calculations for you. So my first question, and I want you to spend a few minutes on this, is what kinds of numbers are there? I just want to know what you might come up with. Have a go. Okay, I've given some examples of numbers on the right. Now this is something I quite like to just sort of draw everyone's ideas on a board. I can't really do that just via video. So here's one I prepared earlier, and I've drawn basically different sets of numbers. So you might have said, oh, well, the first sort of numbers encountered in history are like learning to count on, or when you're growing up, and learn to count on your fingers, 1, 2, 3, 4, 5, and these are our natural numbers. So 7 is a good example of a natural number. um, Whole numbers, okay, whole numbers, they're basically the same thing, but we tend to include 0 in that as well. And actually it took a long time in history for people to accept 0, interestingly enough, because it doesn't really have much function in earlier civilizations. What's the point in saying you've got 0 of something? But it turns out to be very important in our place value system today. Okay, integers, that extends my numbers. Still like sort of whole numbers, but now also including negatives. So -3 would go into the uh, integers set. Notice that 7 also goes into this, so I'm encompassing the natural numbers here. Then I might get onto rational numbers. Rational numbers are ones that I can write as a fraction. That's the definition. So something like 2/5 is a rational number. Whole numbers are also rational numbers because I could write it as 7/1, for example, or -3/1, so they still fit. We then get numbers that cannot be written as fractions, and it's not always obvious to know whether they do or not, but √5, for example, cannot be written as a fraction. I'm not going to show you how that is true. I mean, that's a more sort of advanced topic that is covered in A level, but you just have to trust me, it cannot be done. And actually, nor can pi. Pi is one of the most famous numbers. It is irrational. The proof of that is very long. Actually, I think I've glanced at it, but never, fully understood it. But I accept that somebody else has shown that pi cannot be written as a fraction. Together, these rational numbers that can be written as fractions and these irrational numbers that can't make up real numbers. And actually, this is not technically true what's been drawn here, because there is no real number that is not a rational or an irrational number. So this blue and the red together make all of the green. Just realized I didn't talk about 3.6. That is a rational number because I could write it as 36/10, for example. So it goes in here. Remember, fractions, decimals, percentages are just the same way of writing the same number, different way of writing the same number. Okay, that just leaves complex numbers, which is quite likely to be a new word for you. These are numbers that we've not encountered yet, such as the square root of a negative number. Actually, that is sort of the basis of complex numbers. And what we do is we suddenly allow that in maths. We call it I, and then we can write down things like 3 plus I or 4I, and we can do lots of important maths. And actually, you might think, why would you do that? But it underpins so much technology and everything. If you're talking about electrical circuits, people do calculations using complex numbers. That's something that's studied in further maths A level. Not really going to talk about that anymore, but I think it's quite interesting to talk about. Okay, a few things I've not spoken about. I've not spoken about things like square numbers or prime numbers. That I reckon those might have been some that you thought of yourself. Square numbers and prime numbers would all be examples of whole numbers, even potentially natural numbers. So, you can get sets within these little sets. This just leaves numbers like this. And actually, we can simplify. We know how to cube root 27. It's just 3. So that would be an example of a... Oh, sorry, my pen is up in the shocker. That would be an example of just another, actually, natural number. Cube root of 16. Okay, we'll come back to that. Root 64 is equal to 8. That's also a natural number. So what about the cube root of 16? Actually, if you were to get your calculator out for that, I know I said no calculators, but you will see, if you work that out, that you get 2.519. And this is another irrational number. Now, okay, there's something I've not yet talked about. I've not talked about the word of surds. And basically, surds are within irrational numbers. So I can split my irrational numbers into things that involve roots but are irrational, and things that don't involve roots and are irrational. So basically, root 5 and root 16, sorry, the cube root of 16 are surds. They are when you are taking the root of something and you don't get a nice answer. Whereas root 64 and the cube root of 27 are not surds. They might involve roots, but I can simplify them to nice numbers. So just think of surds like basically a root that you cannot simplify. And we're going to do lots of maths with them. And there's sort of a way of keeping things exact, because often when you do calculations, you might get an answer like 1 plus root 2. You put that in your calculator and you round it. But actually, this is the more exact form, just to leave it like that. Okay, so some more examples. Here are some examples. So root 2 can't be simplified. It's this really long number that goes on forever. It is a surd. So is root 3. Root 4, however, can be simplified, so it's not a surd. Root a quarter is the same as a half. It's not a surd. Whereas something like the cube root of 11 is. Cube root of 27 I've already spoken about, not a surd. The fifth root of 3 is a surd. So hopefully that gives you a bit of a feel for what a surd is. Okay, so we've looked at loads of different number systems basically, and then we've defined what a surd is at the end. And hoping you're happy with that. Talked about what numbers are surds and what numbers are not surds. All right, we're not going to do any sort of rules of surds today. We're going to just play around with them and see, just get a feel for them basically. Discover them in some calculations and use them and think about when can I simplify things and when can I not. So my question is, if we've got this this pin board, a 3x3 pin board, and I've basically connected 3 dots to form a triangle. It just happens to go through this 4th dot as well. What do we know about this triangle? Pause the video and have a think about this, please. Okay, there's a few things that you might be able to calculate from this. I'm actually just going to jump to the one that I want to focus on today. We could try and work out the perimeter of this triangle. How are we going to do this? Well, we're going to say that each of these lengths is 1. So from a dot to a dot like this is 1. However, if we're going diagonally, it's not going to be 1. It's going to be further, because if I go up and I go up and along, it's going to be a further distance to go like up and along, basically. So how can I work out these other lengths? Well, first of all, actually have a think about that. Okay, the answer is that if I want to work out this length here, I can draw a little right-angled triangle where the red line is now the hypotenuse. So I know I've got 1 as the base, 2 as the height, and I can use Pythagoras' theorem. I can do 2 squared plus 1 squared square rooted, and that's going to give me the square root of 5, which is a surd. Great. Okay, I've got square root of 5 as the length. I've then got to do the same for this one here. I'm trying to use green. Okay, green's working now. I've got another right angle triangle. This time, height is 2, the base is 2. It's going to be 2 squared plus 2 squared, square rooted, and that's going to be square root of 8. So my perimeter is going to be 1 plus root 5 plus root 8. And this answer, we're not going to put that in a calculator. That is our answer. It's a surd. Another example of a surd. Just because I'm adding a nice whole number to it, actually, this is still classed as a surd. So my question for you is, if I got this 3x3 pin board, what different triangles can you draw on it? Okay, so you've got to connect the dots. You can't just draw a triangle like this. Okay, that's meaningless. What I want you to do is use the dots on the pin board as the vertices. So see if you can find them all. Spend some time on it. And then I want you to calculate the perimeter of each of your triangles. Please have a go. Okay, hopefully you enjoyed that task. I think it's a really good task because it just gets you investigating whilst exploring the idea of surds. So here are the 8 triangles that I found. I didn't specify before, but what I meant was, so for example, this triangle here and this one would be the same. It's not really interesting to kind of draw it in a different orientation. That's how many triangles we've got. So these are all the 8 ways of doing it. I don't think there are any others. And then you should have tried to find the perimeter. We'd already done this one, okay? But these are my answers for the other ones. So see if you agree. Notice if you get root 2 plus root 5 plus root 5, we can write it as 2 lots of root 5. So this is kind of starting to get into some of the rules of surds. Just like x plus x is 2x, root 5 plus root 5 is 2 root 5. It's just an example. I've just basically replaced x by root 5. So hopefully you're happy with that. Okay, sometimes, but you can't combine root 5 and root 8 into, say, root 40. That makes absolutely no sense, but we'll be talking more about that. Okay, this one I got 4 plus root 8. I'm just going to show my other answers. See if you agree and let me know. Okay, so hopefully you've managed to find those. We've left them all exact. Okay, they could just be simplified. A few of them could be simplified, most of them couldn't. My only final question, if you have the time, is what other quantities can you calculate for the triangles? So I want you to pause the video and have a think, and then I'm going to give some suggestions. Okay, so some suggestions are you could try and find the area of these triangles. You could order them from smallest to largest. You could even try, this is a trickier task, in ordering the perimeters from smaller to larger, because that will give you some inequalities. For example, the fact that 4 plus root 8 is going to be bigger than 1 plus root 2 plus root 5. Sometimes it's not so easy to see, like if you add them up, which is going to be bigger, but you can have a go with that. You might think, well, how many triangles that are like this can I put on there? I know we ignored that before, but I think for this one we could put one there, we could put one there, we could put one the other way round. You might want to think how many there are, and you could look at rotational symmetry. Just think of other mathematical questions that you might be able to do. Otherwise, well done. That is our first lesson on surds, where we basically talked about the idea of a surd, but in some depth, relating it to other kinds of numbers. We've introduced what is a surd and what's not a surd. We found out later on that this sort of thing is also a surd, and we did some calculations on a pin board as well with triangles. Brilliant.